Welcome to the class of antenna and wave propagation, and this is one of the video lecture, and in this lecture we will discuss about the topic about the antenna that is known as the YAGI UDA antenna, and the, if time permits, we will also discuss about the long wire antennas. Now this YAGI UDA antenna is name is mainly based upon the name of the scientist. These two scientists have developed this type of antenna, that is a YAGI UDA antenna, and this YAGI UDA antenna is generally mainly used for the TV reception over the last few decades. Now for the TV reception we are using the parabolic antennas, but in earlier days these type of antennas are used for the TV reception, and it was the most popular and easy to use type of antenna with its better performance, and and this performance can be described in terms of the high gain and the directivity. So as this antenna is mainly used for the TV reception, so frequency range is around, operating frequency range of this YAGI UDA antenna is 30 megahertz to 3 gigahertz, which is also belong to the VHF band and the UHF band. So this YAGI UDA antenna mainly consists of three elements, and this first element is known as the driven element, and this driven element is connected to the power supply of the system, and that system can be what? Can be TV or anything. Clear? This one is the first element, and the second element which is connected behind this driven element is known as the reflector, and the third element which is placed in front of the dipole antenna or driven element, this driven element, or and in the antennas which the conductor which is placed in front of the dipole antenna or driven element are known as the, this third element is known as the directors. Clear? So this power is supplied to this driven element, so that is why it is also known as the active element. And these reflector and directors are not connected to the power supply, so these are known as the parasitic elements, means their feed is totally dependent upon the radiation by the driven element. So this YAGI UDA antenna design has a dipole which is the main radiating or the driven element. Further, their parasitic element, these parasitic elements are added which are not directly connected to the driven element, means this parasitic elements, reflector and the directors, these are not directly connected to the driven element, so these are known as the parasitic elements. These parasitic elements pick up the power, means pick up their feed, and that feed is what? Power. Pick up the power from the dipole and re-radiate it in the forward direction. Clear? Now when these are radiated in the forward direction, the phase matters, and the phase is in such a manner that it affects the property of RF antenna as a whole, and causing the power to be focused in one particular direction and removed from the others. Now see, let's say in a simple way I can say that, let's say this is a dipole antenna, this dipole antenna radiates its energy in this direction. The radiation pattern of this dipole antenna is like this. This is the radiation pattern of dipole or active element. Okay. Now, when reflectors and directors are placed in behind the and in front of the this driven element, like this one, so the radiation pattern of whole antenna comes out to be, ideally radiation pattern comes out to be the in the forward direction, and there's some back lobes will also be there. If I say that is a practical condition, clear? So you will see there that this dipole antenna radiates its energy in this direction. But after getting, so these are the parasitic elements. These parasitic elements get excited due to the energy received from the driven element. So that's why these are known as the parasitic elements, which gets excited after getting a signal received from the driven element. So when the signal strikes in this move towards this reflector reflects back the energy in the forward direction in such a way that after getting reflected, the wave already which is traveling the forward direction and the wave which is after getting reflected in the forward direction, these waves will get additive in a such a way that their phase will also be a constructive pattern. Their phase will make a constructive pattern. Clear? So this parasitic element, the phase is in such a way that it affects the properties of the RF antenna and causing the power to be focused in one particular direction and removed from the others. The parasitic elements of the YAGI UDA antenna operate by re-radiating their energy in a slightly different phase to that of the driven element. They re-radiate, these parasitic elements re-radiate their energy in a slightly different phase to that of the driven elements. So in this way, the signal is reinforced in some direction and cancelled out in the other direction. Therefore, amplitude and phase of the current which is induced in the parasitic element is dependent on what? When the signal received from the main driven element. So reflector and directors get excited, and they are getting excited and in such a way that the amplitude and phase of the current that is induced in the parasitic element is dependent upon the length and the spacing between them and the dipole. Clear? Means the phase, amplitude and phase is dependent upon what? Amplitude and phase of the reflected wave which is getting reflected by the reflector, or the wave which excites to what? Which excites the directors, or in such a way that the amplitude and phase is introduced in the pattern, it is dependent upon the length and the spacing between them. Means the length of these elements matters for constructive YAGI UDA antenna and for making a amplitude and phase in such a way that they are getting induced in the forward direction in a additive in a constructive pattern. Clear? And this spacing between this and these elements is very important for construction of YAGI UDA antenna. So there are mainly three types of antenna which I have already told you. First one is a driven element, is a YAGI UDA antenna to which the power is applied. Another one is the reflector. This YAGI antenna will generally only have one reflector and it is placed behind the main driven element. Clear? Next one is the director. These director can be one or more, are placed in front of the driven element in the direction of maximum sensitivity, such that these director will add up their gain, means they will increase the directivity of the antenna. So now the figure of this YAGI UDA antenna. This one is the stand on which the conductors are placed. These are the normal conductors. This is a dipole antenna, which is a folded dipole antenna. Here is used or described in the figure. And the main is power. The power which is supplied to this driven element is connected to the TV set. Clear? And the conductor which is placed behind the driven element is this one, and that is known as the reflector. And the antenna, the conductors which is placed in front of the driven element are known as the directors. So you will here observe that from the figure you will observe that these are the directors and this is a reflector and this one is the main driven element, that is a dipole, folded dipole. Now you will see here that you will observe from the figure that this length of the dipole antenna is this length of the reflector antenna is greater than the length of the main driven element antenna, that is a folded dipole antenna, and these directors have the length less than the length of this folded dipole antenna. You will hear that the length of the reflector is greater than the driven element and the length of the directors is lesser than the length of the directors is less than the length of the main driven element. So generally we place the basic element of the YAGI UDA is the half wave dipole, which is placed horizontally, known as the driven element. In order to make the unidirectional antenna, additional rods elements are placed on either side of the antenna. I have already told you these reflectors and directors are mainly placed to make the antenna radiation pattern should be unidirectional. So these elements, these parasitic element which is placed in front or behind the director element, these elements have no electrical connection with the dipole and these are known as the parasitic elements. So there are some design equations, design formulas for constructing a YAGI UDA antenna. First one is the length of this dipole antenna is equal to 143 by f, and length of the reflector is equal to 152 by f, 152 by f, and this frequency is expressed in the form, should be in the form of megahertz. Then the output will be in the form of what? Meter. Clear? The director length will also be 137 by f and second director length is 134 by f, and the length, or if I I want to describe these constructor equation in the terms of lambda. So length of the successive directors means length of the D1 or D2 or D3 successive directors. These are the successive directors D1, D2, D3 is reduced by the 2.5%. Clear? The spacing between the directors should be equal to what? 0.13 lambda, and the spacing between the director and the spacing between the director and the dipole should also be equal to 0.13 lambda, and the spacing between the director driven element and the reflector should be equal to 0.25 lambda. These are the design equations for constructing a YAGI UDA antenna. Or you can also say that length of driven element is generally considered to be as a lambda by 2. Length of the reflector is equals to 105% of lambda by 2, or you can say lambda by 2 plus में 5% of lambda by 2. Clear? And the length of the director 1 is equal to lambda by 2 plus में 4% of the lambda by 2, or you can also say plus नहीं, it should be minus, or you can also say that it is 96% of lambda by 2. Clear? So the length of director 1, similarly you can say that the length of director 2 as we know that the length of successive director is reduced by 2.5%, it is equal to 97.5% of 96% of lambda by 2. Clear? Or you can say 97.5% of length of director 1. So this is a radiation pattern of the YAGI UDA antenna, practical or not ideal, you can say. This is a practical radiation pattern of the YAGI UDA antenna, that is equal to this one. There are some back lobes and the side lobes. Clear? But you will observe here that the directivity of YAGI UDA antenna is more than the directivity of driven element or you can say lambda by 2 dipole. Clear? So this is a radiation pattern, means there's some back lobe also will be there, but the main lobe is in this direction, that is in the direction of, you can say, if I want to say that is 0 degree, so 0 degree to in the 0 degree direction. Clear? Somewhere it is also written that this is also 0 degree, so you will see here that is equal to 270 degree. Sorry, 360 degree. 270. Clear? So these are the applications of this YAGI UDA antenna. It is mainly used for the TV reception, used where the single frequency operation is required. Now Now next one is the YAGI UDA modifications, means they are some parameters are added onto the YAGI UDA antenna to modify its features. Means there are some features to be added in the unique in the YAGI UDA antenna, so that we will get the modified YAGI UDA antenna. Clear? So first one is the circular polarization with YAGI UDA antenna. Means that there will be a YAGI UDA antenna, and that YAGI UDA antenna is having a polarization, that is a circular polarization antenna. So you will see here that this is will be a act as a reflector or driven element, and the power which is supplied to this wire or conductor in the shape of helical. So these are known as the driven element in the shape of helix. Clear? And this is a act as a reflector, this is act as a driven element. So there will be a need of what? Other parasitic element that are the directors. So when these conductors are placed like this, so these cross detectors are mainly also used for what? High directivity. So these are known as the cross detectors. Clear? Now next one is the next modification, Landsdorfer shaped dipole antenna. Means you will observe here that different type of radiation pattern can be formed. Radiation pattern can be formed using a YAGI UDA antenna. Now second one is the Landsdorfer shaped dipole antenna. Let's say this is a folded dipole antenna whose length is equal to 3 lambda by 2, and when this length is equal to 3 lambda by 2, that is greater than the half wave dipole. So the radiation pattern of this dipole antenna will be equal to what? Like this one, in the shape of 8. Clear? So means the radiation will take place here like this one. Clear? Now next modification, if I change the length of this dipole antenna to like this is lambda by 2 antenna, and this is also lambda by 2 antenna, and these are the another wire, or that is as it is a folded dipole antenna, the length of this will be equal to lambda by 4. Clear? Now so the radiation pattern of this folded dipole antenna is this one, not of this one. This is radiation pattern of what? This antenna, when the antenna length is reduced in one particular direction, that is in the lambda by 2. Clear? And this radiation pattern which is having a overall length is 3 by 2 lambda. This is having a radiation pattern like this one. So to improve the radiation pattern of this antenna, we will change the length of the dipole antenna in one particular direction. So you will get this type of antenna, means which is having what? No side lobes or no other lobes, only lobe in the 0 degree or 180 degree. Now next modification, if I want to just improve this radiation pattern in the unidirectional antenna like this one. So at that point this YAGI UDA antenna consists of driven element. This driven element is in the shape of this one, and these are the directors and these are the reflectors. Clear? So you will here observe that the radiation pattern is what? Unidirectional in only one particular direction. Next point is the next modification is the square corner YAGI UDA hybrid antenna. Means there will be property of YAGI UDA antenna plus में properties of what? Corner antenna. As you know said that this will be a, if I want to open this, let's say this is the main dipole antenna. When this antenna is placed like this one, so this type of antennas, and the signal is propagated, radiated by this dipole antenna, and these are the conductor which is attached to each other in the shape of V, or you can see in the shape of V. So the wave which is getting reflected, which is getting strike onto this square corner antenna, these waves get reflected back into the same direction. So this is one of the modification. This is a modification. These are the reflector, widespread reflector. These are the what? Driven element, and these are the, so these are the directors, and this is a one of the, here it is a driven element. So this one is YAGI UDA antenna with its square corner property. Now next one is the next topic of the today's lecture is the long wire antennas. Now see, if I say what are the long wire antennas, these are the long wire antennas which is having a length greater than the half wave dipole or n into lambda by 2, means whose length is greater than lambda by 2 or length is greater than n into lambda by 2, and this length, this n is integer number. Okay. So there are two types of long wire antennas. There are two properties which is associated with the long wire antennas is the resonant antennas, and another one is the non-resonant antenna. Now see, let's talk about the resonant antenna. These resonant antennas are also known as the unterminated antennas, and these non-resonant antennas are known as the terminated antenna. It means terminated antenna means there will be a impedance matching. Unterminated means the output, the antenna terminals are not properly terminated, and these type of antennas are known as the unterminated antennas. So resonant antennas are those in which standing waves exist along its length, means where the standing wave will exist and absence of terminal impedance, it means that there is no matching and their radiation pattern is bidirectional. The radiated wave move in two directions, it is in the both direction, incident and the reflected waves, like this one. Let's say this is a transmission line. This transmission line is tapered and forms what? Horn antenna. Clear? So if I say that resistance impedance obtained at the terminals of this antenna matches with the impedance of space, then if there is a matching between these and that means there is a load resistance will be there, that is RR you can say, or load resistance will be there, which makes it coupling with the space antenna. Clear? When these terminals are get what? Properly terminated, which means there will be no standing waves will be there, and the radiation pattern means there absence of terminal impedance, there is no matching, and the radiation pattern is what? Bidirectional. And the non-resonant antennas, that means the waves which is getting in the forward direction, hence do not form a standing waves. Radiation pattern here is what? Unidirectional, and the radiated waves in the forward direction. We will discuss this topic also in the next class for further details. What are the resonant antennas and the non-resonant antenna in the detail, and the long wire antennas. The book which I have referred for preparing these slides is Antennas for All Application by the J.D. Cross. Thank you.